In this section, 7.1, we will discuss momentum. Now, one might think that momentum is just as simple as velocity, but actually it's much more powerful. For example, with light, the speed of light is always the same, but the momentum of the photon with light changes quite a bit. It turns out that momentum is a more fundamental constant or concept than velocity is. Momentum is defined, we use the symbol P for momentum almost always, as the mass of an object times its velocity. And it's a vector because it's going to point the same direction as the velocity but be proportional to the mass. And of course, with respect to a photon, although it has no mass, there's still another definition of momentum that works for the photon just as well. This is a very fundamental concept. If we take our standard football player, here he is running along, and as before, we have him going at Olympic speed, the track record, at about 10 meters per second, and that will be his velocity. And he's going to have a mass of 220 pounds, which is exactly 100 kilograms. And we can see from that his momentum P of the football player, is going to be 100 times 10, or 1,000. Now, there are no special names for these units. It's a kilogram meter per second. So kilogram meter per second are the units for momentum, and we don't have any other special name for it, like a Newton or a joule or a watt or anything like that. Now, one of the most special things about momentum is how internal forces cancel. Believe it or not, this is a very, very important and fundamental concept in physics. That if we want to study something like a baseball, and this ball is thrown, that we do not have to know how all of the atoms and molecules are moving around in order to talk about this motion mathematically. We can instead use what is called the center of mass and look at what its velocity is. In other words, we could have a coordinate system that points to r, the center of mass. We could look at the velocity of the whole system, the momentum of the whole system, and the only thing that would disturb this are the outside forces external. That means that all these internal forces, nuclear, atomic, everything else, elastic spring, oscillations in the crystal lattice, none of those will matter. They will all cancel. And I really need to show you where that comes about, because what we're going to end up with here is the fact that for this baseball, the change in momentum over the change in time is going to equal to the external force on the system. In other words, we do not have to worry about internal aspects. We can treat this as one large object with momentum P, mass capital M, velocity capital V, located at a position R, and it will respond only to the external forces and not to the internal forces. I want to prove that to you. We have to use some calculus to do that. And we know what the total momentum is. The total momentum P is the sum of all the momentum of the individual particles. This could be, of course, trillions and trillions of these particles, even more than that, Avogadro's number, these atoms and molecules that are inside, or collections of pieces or fragments of material. And this, of course, is a vector sum, and that gives us our total momentum for any system. It doesn't even have to be a solid baseball. It could be a piece of fluid or gas. And now what we want to do is we want to look at the time derivative of that momentum for the whole system. And it, of course, is going to be the sum over I of the derivative of pi with respect to t. Now, the derivative of the momentum of each object depends upon two things. This is going to be the external force on object I, so it's going to be the sum over j, so it's the sum over I, d by dt, of the sum over j of all the forces on I. Well, what is that? It's the force of j on I summed up over all j's. In other words, the force due to all the other particles add up to push on this particle I, plus another force, and that's the force external on the system, the external force. And now if we take this, we'll notice that this is the force just on the particle I. Now if we add all this up, what we get is we get d by dt of the sum over I and j. I've moved the sum over I to the sum over j of fj onto I, plus d by dt of the external force, sum over I of the forces external. In other words, these are forces that come from the outside, like the wind on the ball, or someone's putting a pressure on the ball from some point of view, or gravity pulling on the ball. These are all the external forces. These are all of the internal forces, where one molecule pushes or pulls, or one atom pushes or pulls on another one. Now if we look at this, do you remember Newton's third law? It said that the force that particle I pushes against J is equal to the force that J pushes on I. Therefore, when we sum all these up, that has a negative sign in it, we get F of I onto J, and then F of J onto I is the negative of that. So for every pair that we have one that's a negative of that pair. Therefore, this whole thing sums to 0. And we get the result out here that dP, momentum of the whole system, dt, dP dt, it's from right here, for the whole baseball is equal to this d by t is not supposed to be there. I apologize. I pulled a derivative over here, and it wasn't supposed to be there. So this is the sum over I and j of all the external forces, and now we're summing up this force here. Let me get rid of this d by dt. And when I add up these forces, I get the total external force over all the particles I, so it adds up to the total external force. And that's exactly what we wanted to prove. I'm sorry about that. I got carried away with my d by dt's here, putting them all the way through on both sides. They don't go over to the force side. The force stands by itself, and we never look at the change in that force. We do look at the change in this momentum, and we have now proved this very important result, that a composite system behaves as though it has a total momentum P that responds with its derivative to the total external force that's put on the system. And we don't have to worry about or even know what those internal forces are. Now, this is worked out explicitly in your notes here, and that's the critical thing that we need. Consequently, if we have any system of particles that's closed and there's no external force on it, we find that if there is no external force, then this vanishes, and dP total dt is equal to 0, which means P is conserved. P is conserved as a vector. So the momentum of a closed system is conserved if there are no external forces. This is very important because otherwise we would have to understand all the molecular forces before we could even work out the trajectory of a cannonball that was shot out of a cannon. And that, of course, is not true. This is a most important result for physics.